And I can share my slides with you. Now let me know if you are able to see my slides or not. Are you guys able to see my projected slides? Shared slides. Okay, someone tell me if you're able to see my slides or not. All right, okay. Let's get started with the lecture here. So we are going to continue our conversation on solving a system of linear equations. We formulated a matrix equation earlier with AX equals B, A containing the coefficients of your unknowns, X containing a vector of unknowns, and on the right hand side, B is a vector of right hand side constants. So far, the way we have been solving for the vector of unknowns X is by forming an augmented matrix. The augmented matrix is formed by using the coefficient matrix A and the right-hand side constants B. And then we go through the reduction process, row-reduced echelon forms or the echelon form, and then we try to look at the solution set. And then we can comment about whether it has infinitely many solutions, no solution, or a unique solution. So that's what we have been seeing so far. Today we'll try to adopt a slightly different method to solve for the vector of unknowns X. So the way we are going to do this is by using matrix inverses. So X can be found by finding the matrix multiplication of A inverse and B. So we are going to learn how to find the inverse of A first, and then we'll multiply that with B to find X. So that's the method that we are going to look at today. So in order to invert the matrix, we need to look at how we can do it for 2 by 2, 3 by 3 matrices, or any squared matrix in general. So we'll be limiting our discussion to square matrices. So inverse matrices, what is the definition? So if A is a square matrix, right, so we are limiting it to square matrix here. Let me pick a square matrix. And if there is a matrix B that can be found such that the matrix multiplication of AB is equal to the matrix multiplication of BA, and if that happens to be identity matrix, then A is invertible and B would be the inverse of A. So AB should be the same as BA, and both of those multiplication products should end up in the identity matrix. So identity matrix would be a matrix with unit vectors as your columns. So let's try to look at an example here to see how this would work out. So A over here is a square matrix. The size over here is 2 by 2. Right, so clearly the size over here is a 2 by 2 matrix. And I'm assuming that there is another matrix, a square matrix B with the same size, 2 by 2, 2 rows, 2 columns. And let us see what happens when we multiply A and B, right? So if I multiply A then followed by B, AB, then I'm putting the A matrix here, then I have my B matrix here. And if you go through the multiplication process for matrices, so the way you get, say for example, this element which belongs to the first row, first column element of the answer, the way you would compute that is by taking the first row of A and doing a dot product with the first column of B. So if you see here, you are doing 1 times 7, which is 7, minus 6, and you get a 1 there. And similarly, if you run through the numbers for all the other values, 4 of them, you will see that the result will be an identity matrix size 2 by 2. So I can call that I sub 2. And now let's take a look at what happens when we try to find BA. So I'm putting the B matrix first and then A, same matrices. And if I do the math over here, again, I will get an identity matrix. And we can check another element here. Let's say we check for this 0. How do we get that 0? That is present at row 1, column 2 of the answer, of the product. So I'm going to take row 1 of B and do a dot product with column 2 of A. In that case, I'm going to get 14 minus 14, and I get a 0 there. Similarly, you can fill in all the others. You should get an identity matrix, and you are getting an identity matrix, same size, I2, right? So in this case, AB equals BA equals identity matrix, both of them, which means that B is said to be the inverse of A. So that's the conclusion that we are drawing here. B is the inverse of A. Now, if B is the inverse of A, let's try to notice a little bit of a pattern here. With 2 by 2, you can do this. What did we do to the diagonal elements? We simply swapped the diagonal elements, and the off diagonal elements over here, 2 and 3, we just multiplied them with a negative sign, -1, right? And that's how you get the inverse of the 2 by 2 matrix. But you also have to divide that by the determinant of the matrix. And in this case, the determinant happens to be 1 times 7 minus 3 times 2, which is 1, which is why you don't see a 1 here, right? So let's take a look at more examples, and we'll talk about what all goes into this. There are two things that are involved: determinant of a matrix and adjugate of a matrix. So let's see. B is right now an inverse of A. The next thing that we are going to talk about is the fact that the inverse of a matrix is unique. So if you wanted to invert A, for example, you would get exactly a unique one particular matrix for the inverse of A. So if A is invertible, and A is invertible if its determinant is non-zero. So let me just write that. A is invertible if determinant of A is not equal to 0. Then we can say that it is invertible. And the determinant of a matrix is computed. Let me do it for a 2 by 2 case. So for example, I have A as some A, B, C, D, 2 by 2 matrix with some values. Then the determinant of this matrix is going to be A, D minus B, C, right? So I'm doing A, D minus B, and let's see. And that's how you would find the determinant of A. And when you go for A inverse, the inverse of A, it would simply be 1 divided by determinant of A multiplied by the adjugate of A. And in this case, the adjugate of A is simply, so you have 1 divided by determinant of A was what? AD minus BC. And adjugate of A is simply switch A with D. So you have D here, A here for the diagonal elements. And then you multiply with a -1 for the other two. Negative B, negative C. So that would be the adjugate of A. Let me just highlight this. The adjugate of A over here is that. And then the determinant of A we computed to be this, which we substituted over here. So this equation over here, this is a general equation. This is applied for any size matrix here. A inverse is 1 divided by determinant of A multiplied by the adjugate of A. It is pretty simple to do it for the 2 by 2 case, which we have done over here. So as you can see, AD minus BC happens to be in the denominator, and we would want that to be a non-zero value so that A inverse can be computed. So A is invertible only when the determinant of A is non-zero. So A is invertible, we have to assume that. Then the theorem says that it has only one inverse. And we are going to prove this by contradiction. So let us assume that there are two matrices, B and C, and both happen to be inverses of A. So we are going to see if B equals to C or not. If B equals C, then there is only one inverse. But if B could be different from C, then the inverse is not unique. So let us see that what happens when we assume that both are inverses of A. So if B is inverse of A, then we can write this: BA equals identity. And if C is the inverse of A, then we can write AC equals identity. This is from the definition of identity matrix, which we have written over here. For the first one, I'm using this, and for C, I'm using this. Let's see. Now we use the fact that matrix multiplication is associative, and we have proved this in a good amount of detail in the previous lecture. BAC, right? If so, suppose you were trying to multiply B times A times C, you can do this B times A times C, or you can do this as B times AC, right? We have seen this before. So let's try to look at BAC over here first, and then the other one is BAC the other way over here. And because we are assuming that both are inverses of A, if BA times BA is identity, AC is identity, then BA times C should equal BAC, right? So we know that from matrix multiplication is associative. BA, as you can see here, BA is identity the way we have assumed. So instead of BA, we are substituting identity. An identity matrix multiplied by C, any matrix, is going to give you the same matrix back. So in the properties of the identity matrix in the previous lecture, we saw that identity multiplied by any matrix gives you back that same matrix again. And also, if you multiply it in a slightly different order, we are multiplying AC first and then B. What do we have? B times AC. AC equals I, because we have said here. So this results with BI equals B, right? So when we did BAC, this should equal this because of associative property, and the result in both cases became C over here, B over there, which means that we must have B equals C. So if you assume that there are two different matrices that are inverses of A, by using this proof, we have proved that both those matrices are exactly the same, which means by contradiction that the inverse of A is unique, provided A is invertible. Now let's take a look at 2 by 2 matrices. How do we find the inverse of that? I have denoted the inverse of a matrix by using a superscript of -1 for the matrix. And I've already done this sort of manipulation, so let me just go through the theorem here. I'm assuming that my matrix A has 2 by 2. How did you remove I? So I is an identity matrix, right? So suppose if I do I times any matrix here, let us say M, it gives you M. And we can prove this. So let's say I wanted to prove this, right? So let me remove this and let me add a slide here. Let me add a slide after. And let us say I have an identity matrix multiplied by any matrix B, right? So let us take a 2 by 2 case. So I have 1, 0, 0, 1 multiplied by any arbitrary matrix. I will say some A, B, C, and D, right? Could be any matrix here. So what does this give you? Well, you have this multiplied by this to get the first row, first column element in the answer. That would be A0. So that will give you A. Then it will have B0. It will give you B. Then it'll have C here and D here, right? So you will get back the same matrix B. And similarly, you could do B times I and you will get back B. So if you did A, B, C, D here and then you did identity, you would get back A, B, C, D. So by running through the multiplication of these two, by doing the dot product between each row and each column in be an identity, you can prove this, that it will be equal. So I hope that answers the question that I can remove the identity matrix. And I did that over here, and I did that over here as well. All right, let's move on. Okay, so we are coming to matrix A. I'm assuming that matrix A has 4 elements, 2 by 2 size, A, B, C, and D. And the determinant of A, I've already told you guys that it is AD minus BC. For A to be invertible, AD minus BC has to be a non-zero value. So I'm assuming that it is, right? If a determinant of matrix A, AD minus BC is non-zero, then we can say that A is invertible. And the way you do that is A inverse is going to be 1 over the determinant, right? This is the determinant. And then you have the adjugate of A. And the adjugate of A is simply looking at the 2 by 2 matrix in A, switching the diagonal elements, principal diagonal elements, right? AD is switched with DA, we have swapped them, and then multiplying the other two with a -1. Now let's try to verify that A, if you multiply by A inverse, do you get identity matrix or not? And similarly, if you took A inverse and you multiplied by A, you should get identity matrix again. So let us try to verify this for the given A inverse. So we are going to assume that A inverse is this, A is this. Let us check whether A times A inverse will be identity or not. So let me zoom in over here and let me write this down. So I'm doing A times A inverse, which means that I have A first, A, B, C, D, 2 by 2, and then A inverse is going to be, let me bring out the factor up front. That's a scalar value, right? So I can bring it out all up front. 1 divided by AD minus BC. That is present in the A inverse matrix. And then I have the adjugate of A here. So this is D, A minus B minus C, right? So all of this, let me use yellow here. So this along with this belongs to A inverse. And the other guy A is over here. Now let's try to carry out this multiplication and see whether it turns out to be identity or not. So over here, what do I have? I have 1 divided by AD minus BC. That remains as is. And then I'm going to do a matrix multiplication. So when I do that, first row, first column, dot product, I have AD minus BC for the first element. And then I have, for the second element, what do I have? Minus AB plus AB plus BA, whatever. And then I have CD minus CD. Next, I have minus BD plus AD. No. Minus BC plus AD. And you can see that this goes to 0. This goes to 0. And both these values here and here, when I divide this by AD minus BC, each of those elements will cancel out, giving you an identity matrix of size 2, right? So this will be 1, 0, 0, 1. So this sort of verifies this. And similarly, you can verify A inverse times A as well. Just switch the order of those two matrices. And if you carry out this sort of a similar proof here, you will see that it turns out to be an identity matrix. So the inverse of A, as long as it is invertible, right? The determinant of a matrix A, if it is non-zero, then it is invertible. And if it is invertible, you take the matrix multiplied by its inverse, you get back your identity matrix. So, you guys can think of it like if you take a number 5 and you multiply it with its inverse, you get a 1, right? So that's what we do in arithmetic algebra. And that's what we are doing over here with matrices. Now we don't have one number, we have an rectangular array of numbers. And in this case, we are considering a square array of numbers. Questions about this? So to find A inverse, find the determinant, find the adjugate. 1 over the determinant of A multiplied by the adjugate of A gives you A inverse. And for a 2 by 2 case, it is pretty straightforward to do that. As the order of the matrix increases, as you go to 3 by 3, 4 by 4, the math involved to find the determinant as well as the adjugate keeps getting complicated, more and more complicated. And you can see a very sharp jump in the complexity of the math when you go from 2 by 2 to 3 by 3. All right, let's move forward here. Inverse of products. Let us take a look at what happens when you multiply two matrices A and B and then take the inverse. The theorem says that it would result in doing a matrix multiplication of B inverse times A inverse. Now you see the order matters over here. First, what are we doing? We are assuming that A and B are both invertible matrices, which means that the determinant of A is non-zero, determinant of B is non-zero. That's what this means. And I'm assuming that they are of the same size. So 2 by 2 is the same as, Andre asks a question, if the ones and the zeros are switched, would it still be an identity matrix? If the ones and the zeros are switched, no, it will not be an identity matrix. So identity matrix is defined as it has to have ones in the principal diagonal. This is off diagonal elements. So you cannot switch the zeros and the ones. That would not be an identity matrix. So you need to have ones in the principal diagonal. Like you do in the reduced row echelon form. Let's see, if I go here, I have, okay. So if I wanted to do this, multiply A and B first. I've already assumed that A is invertible, B is invertible, and they are of the same size. If I assume all of that, and I'm now trying to find A times B and then invert the product, the theorem says it is going to equal to B inverse times A inverse. You have to switch the order of the matrices while you are inverting each of them. So you do B inverse, put that up front, and then multiply it with A inverse. And finding B inverse and A inverse again involves finding determinant of B, finding adjugate of B, finding a determinant of A, finding adjugate of A, and then doing B inverse multiplied by A inverse. So you're switching the other order. The same thing that we did for even the transpose, right? So AB transpose was B transpose multiplied by A transpose. We looked at that property in the previous lecture. It's a similar result we get for the matrix inverse. So let's try to look at whether it would be true or not. So what I'm doing over here is I'm trying to assume that this is true, right? So if AB inverse is B inverse B A inverse, let us start with this statement: AB equals AB, right? I'm starting with AB equals AB. That's pretty straightforward to assume. The product of two matrices AB should equal the same thing, AB. Next, what am I assuming here? I am multiplying both sides with AB inverse on this case and B inverse A inverse on the right hand side. And if all goes well, it should satisfy. So B inverse A inverse over here multiplied by AB, I can use the associative property of matrix multiplication to keep the order but do the matrix multiplication in a different order. So here I was doing AB first, and then I was doing B inverse A inverse second, and then I was trying to multiply these two together. That was the third step. Because of associativity of matrix multiplication, I can keep the B inverse front. I can move the parentheses to A inverse A here. I have to maintain the order of the matrices, and then B, I'm putting it out. Now, A is invertible. If A is invertible, we looked on the previous slide that A inverse times A will be identity matrix. So instead of writing A inverse A, I'm just going to write identity matrix. So over here, this is going to be equal to identity matrix. And I don't even need to write that because B inverse times identity. So I have what? After this, I have B inverse I B. So no matter what I do, B inverse I or IB, that identity matrix, you can remove it from the equation. You will be left with B inverse times B. B is invertible, so that will also simplify to identity. So what does this mean? This means that AB inverse multiplied by AB came out to be an identity matrix. That is absolutely true because we looked at the previous property where you take any matrix A inverse A, you will get identity. So we know that this is true, which also validates that AB inverse is going to equal B inverse A inverse. So that sort of proves this property over here. Now you can also extend this to many factors. So what if you had 5 matrices A, B, C, D, E, and you are multiplying them in that order? What if you did the inverse of that? Well, in that case, you will have that equal to E inverse, D inverse, C inverse, B inverse, A inverse. So product of the inverses of each matrix, but in the reverse order. Questions here? Okay. The powers of a matrix. So what if I want to raise a matrix A to the 0th power or 2nd power, 3rd power, and so on? So if A is a square matrix, A raised to 0 will be an identity matrix. A raised to P is going to be P factors of A. Matrix multiplied by A, so on, P factors of that when P is greater than 0. So this is where you have A raised to P, right? So A raised to 2, 3, 4, and so on. What about -2, -3, -4, negative powers of a matrix? How do you deal with that? Well, if A is invertible, you can define A raised to negative P, where P is still greater than 0. So we are talking about A raised to a matrix A being raised to a negative power that is going to equal A inverse raised to P, which means that you have P factors of A inverse, provided P is greater than 0. So this is how you deal with positive or negative powers to which a matrix could be raised to. A raised to 0 will be an identity matrix. Now let's take a look at some more theorems of the powers of a matrix. And these are going to follow directly. So the first theorem over here is if A is a square matrix and R and S are some integers, then if you did A raised to R multiplied by A raised to S, that is going to equal A raised to R plus S. Also, A raised to R raised to S is going to equal A raised to RS. So it's very similar to how you would raise any number or any variable to a power. The matrix the raising a matrix to a specific power works exactly the same. This is when A is a square matrix. Next, if A is invertible, determinant of A is non-zero, then A inverse is invertible. So if A is invertible, then A inverse is invertible. And in fact, the inverse of A, you get back A. Let's try to look at this. So I'm assuming that A is invertible, and I'm going to try to find the inverse of A inverse. And let us check whether you get back A or not. And let us do that on the next slide here. So what I'll start off with is sum A. Let me use a 2 by 2 case, A, B, C, and D. And if I'm assuming that A is invertible, determinant of A, assuming A is invertible, this implies that determinant of A is non-zero, then I can write A inverse. What is A inverse going to be? A inverse is A inverse is going to be 1 divided by determinant of A multiplied by adjugate of A, which is going to equal the determinant I know for the 2 by 2 case, AD minus BC. So 1 divided by AD minus BC with the matrix D here, A here, negative B, negative C. That is going to be A inverse. Next, if I wanted to find the inverse of A inverse, then the first thing that I'm going to do is find the determinant of A inverse and also the adjugate of A inverse. So let me just write that down. A inverse is going to equal 1 divided by determinant of A inverse multiplied by the adjugate of A inverse. All right, let's try to find out the two pieces then. Determinant of A inverse, what is that going to be? Determinant of A inverse, and I'm looking at this matrix over here, right? So what is that going to be? Well, I can take the AD minus BC into the matrix. So the way I do scalar multiplication is element by element. So each element gets divided by AD minus BC. Over here I have minus B divided by AD minus BC. And over here I have minus C divided by AD minus BC. And over here I have A divided by AD minus BC. So for this matrix, I'm trying to find the determinant, right? So I'm going to move this over here and I'm going to say I'm trying to find the determinant of this guy. And the way I find that is by multiplying these two guys and subtracting the product of these two guys. So let's do that over here. What do I have? Equals, I have AD divided by AD minus BC squared, and I have minus, there are two negative signs on the product there, so that cancels out. I have minus BC divided by AD minus BC squared as well, which gives me AD minus BC divided by AD minus BC squared, which gives me 1 divided by AD minus BC, which is sort of 1 divided by determinant of A, right? So I know that the determinant of A inverse worked out to be 1 divided by AD minus BC. I was going for inverse of A inverse. I found this. I just need to find adjugate of A inverse. So let's try to look at that. Let me add a slide here. Adjugate of A inverse. How can I find that out? I have to, I'm going to consider this matrix here. That is the matrix A inverse. I'm going to switch these two elements and then multiply with a negative sign over here and here, right? So let me go back. So let me see. Just for the sake of reference, I will copy this from here and move it over here. That is adjugate. Sorry, that's A inverse. To find the adjugate, I'm going to move this over here, move that over there, and then multiply the other two guys with a minus sign, so I can just erase these two negative signs here, right? So that would be the adjugate of A inverse. So I'm ready with the determinant of A inverse. I'm ready with the adjugate of A inverse, which means that I can do A inverse, which is going to be 1 divided by determinant of A inverse, adjugate of A inverse, which gives me what? Determinant of A inverse, what was it? 1 divided by AD minus BC, right? So that is, if you have 1 divided by BC, you simply have AD minus BC now with the adjugate. So let me not even write that. Let me just take this, copy and paste. Okay. Now you can see that when you do the scalar multiplication of this, there is a AD minus BC here in the numerator, and there's a AD minus BC in the denominators everywhere, which will cancel out to give you A, B, C, and D as your matrix. Which turns out to be A as we assumed, right? So this proves that the inverse of A inverse is A. Questions about this? Okay. So let's go back here. So we looked at this. A inverse is invertible, and A inverse of A inverse will be A. And if A raised to P is invertible, then you can say A raised to P, the inverse of A raised to P is the same as A inverse raised to P when P is 0, 1, 2, any positive number there. For any non-zero scalar K, the matrix Ka is invertible with Ka inverse equals 1 over K A inverse. So let us assume that, let's take a look at this property right here. So I'm going to assume that I have some a matrix, say B, and I'm going to assume that that matrix is 1 divided by AD minus BC, some scalar value that I'm multiplying with D minus B minus C A, right? So I'm just considering this to be a K and this to be some matrix A. And we know that this 1 divided by AD minus BC followed by the adjective, this is nothing but, I should write that in over here. This is nothing but inverse of A, right? So if I do this, how do I find the inverse of this? B inverse, which is going to be K A inverse, we know that it will work out to be AD minus BC, and then you will multiply it with 1 divided by AD minus BC, and you have A, B, C, and D, which works out to be A, right? So this, I'm using this for K, this for A, all of this for A. So assuming that Ka is invertible, when I did B inverse, which means I did this, right? Ka inverse, what did I get? 1 over K multiplied by A inverse. So the inverse of A, you get back A, and the K cancelled out. AD minus BC cancelled out with that. So this takes care of the inverse over there. All right. We looked at this, All right, so inverses and non-singular matrices. How do we deal with any non-singular matrix? I'm going to lay out 5 statements that are all equivalent, which means that they're all true or they're all false. So assume that A is a square matrix and it has a size n by n. So 2 rows, 2 columns, 3 rows, 3 columns, and so on. So A is a square matrix. And the theorem says that all the statements are equivalent. So there are 5 statements over here. They are all equivalent, meaning all are true or all are false. So suppose that I say 2 is true. If 2 is true, all the other statements will be true. And if any one of them is false, so for example, A is false, then all the others will be false. So all true or all false. Now, so let me just walk you through the statements here. The first statement is A is invertible. Okay, so if A is invertible, then A is non-singular. So we looked at the differences between singular and non-singular matrices in the last lecture. For a non-singular matrix, what did we say? We said the solution to the homogeneous equation Ax equals 0 has only one trivial solution, which is x equals 0. That's how we defined a non-singular square matrix. So if A is invertible, then you can say A is non-singular. Then we can also say A is row equivalent to an identity matrix. What does this mean? This means that suppose you start with some matrix A, which is a square matrix, and you go through the process of row reduction, right? So you do all those Gauss elimination or Gauss-Jordan elimination to get it down to a reduced row echelon form. And if A is invertible, then that row reduced echelon form will be identity matrix, IN. Well, N is the same size as the matrix that you started off with. So A is row equivalent to an identity matrix. Then the fourth statement over here is the columns of A are linearly independent. So this is the same thing as saying we tied the concept of linear independence with non-singularity in the previous lecture. So if A is non-singular, then we also know that the columns of A are linearly independent, which sort of means that if you take each column of A, suppose the columns of A are V1, V2, V3, and so on, up to VR. In this case, you will have Vn because A is n by n. Then you form the vector equation. What is the vector equation? K1 V1 plus K2 V2 plus and so on up to Kn Vn equals 0. That is the vector equation. That vector equation will only be 0, will only be satisfied when all the k's are 0. In other words, each column in A represented by a vector V1 here is going to be linearly independent of the other. So columns of A are linearly independent. Next, the linear system AX equals B. So this is the system of linear equations. It is going to be consistent, and there is going to be a matrix B. If you know B, then you have some solution to this. So the last statement over here, 5, says if A is invertible, you can invert this, multiply it with some matrix B, whatever you have for the right hand side constants, to find X, and it is going to be a consistent solution. Now, the really long way to sort of prove this is going to be take every statement and prove all the others, which is going to give us a lot of possibilities for proofs. But a simpler way to deal with this is looking at it as implications. So one way to prove this is to show that 1 implies 2, 2 implies 3, 3 implies 4, and so on, 5 implies 1. So if you are able to show that, then we know that all of these are going to be true, or all of them are going to be false. So I'll look at one of them with 2 and 3. So I'll assume that we are given 2, and I will try to see whether 3 is going to be true or not. So we'll show that 2 implies 3. So 2, what does 2 say? 2 says that A is non-singular. So the solution to the homogeneous equation Ax equals 0 is a trivial solution. All the unknowns are 0. So I'm going to assume that. Assume 2, because I'm assuming 2, which means that Ax equals 0, the homogeneous equation, has only a trivial solution. Then we will try to row reduce the n by n plus 1 augmented matrix, which is A followed by 0. So if you look at this, I'm going to try to see this, right? If you look at this, what does this have? This has, how do you solve this system of equation? We will look at A here, and then we will have for the right hand side columns, for the right hand side constants, you will have a 0, right? So that's how we are forming this augmented matrix. Clearly, if A is n by n, if this is n by n, and we are adding only one more column to the right hand side, so the size of this guy, the augmented matrix, will be n by n plus 1. In terms of columns, we have added 1, which is the 0 vector because of the homogeneous equation. So now if you take a look at this, this is a square matrix, right? So if you have a square matrix, what do you have? You will have coefficients over here, right? So you will have a bunch of zeros there. Instead of writing just one zero as a vector, I can say this is going to be a bunch of zeros. How many zeros? N zeros, right? For the right hand side constants, for the system of equations. For A, this is going to be the coefficients, right? So this will be, you will start off with A11, A12, and so on up to A1n, and then you will go down, right? You will have, last one will be AN1, AN2, and so on up to ANN, right? Let me erase this and maybe use a different color here. Right, so that will be your augmented matrix. Here you have the set of coefficients, here you have 0, size will be n by n. Now from this, what can you do? From this, you can start doing row reductions, right? When you start doing row reductions, what will you have? Well, this will not change. All of this are going to translate into a identity matrix, right? So we get leading ones in every row. So all of these are going to be, as you do the row reduction, you will have all of these go to a 1, all the other elements will go to a 0, which means that A will be row equivalent to an identity matrix. Remember, for the homogeneous set of equations, we said if you are going to have the same number of equations as unknowns, then you will have a trivial solution or a unique solution, right? So those are the only possibilities. You will not have infinitely many solutions. So as you're reducing this, you see all of this will translate to an identity matrix. So which is what the condition 3 says. A is going to be row equivalent to an identity matrix. So 2 implies 3. That's one thing that we have said over here. If A is non-singular, then A is going to be row equivalent to IN. Next, let's try to look at the actual problem here. Actual problem is you have the system of linear equations. You're trying to find X, right? So we have coefficient matrix in A, you have the vector of unknowns in X, and you have the right-hand side constants in B. X and B are column vectors. A is a coefficient matrix. What would be the solution for this? Well, the claim over here is X will equal A inverse multiplied by B. That multiplication is a matrix multiplication. Let us try to see whether that is true or not. So because I need to invert A, I'm going to have to assume that A is invertible, which means that the determinant of A is non-zero. Next, if there is X that solves this equation AX equals B, then we must also have, if you just rearrange this, B equals AX, right? So if you start with B equals AX, right, we are starting with B equals AX, that is just the system of linear equations. Let us try to multiply both sides by A inverse. And I know A is invertible, so A inverse exists. So I'm trying to multiply B with A inverse here, AX with A inverse here. I'm just taking this and I'm taking this and multiplying it with A inverse on both sides, here and here. Next, what do I have? I have a matrix multiplication going on over here, which is associative, which means that this is going to equal A inverse A and X. I'm preserving the order in which they are getting multiplied. I'm preserving the sequence in which they are getting multiplied. But instead of doing AX first, I'm doing A inverse A first, associative. A inverse A, we proved that it is identity matrix. X carries over. IX, we have proved that it is the X vector. A inverse B is X. That is the solution, right? So the vector of unknowns can be found by taking the inverse of A and multiplying it with the column vector of B, which has all the right-hand side constants, provided A is invertible. So if A is invertible, you can find the solution as A inverse B. This is a unique solution. This is a unique solution, AX equals B. X is A inverse B. So if I know how to find the inverse of a matrix, then I find that out, and then I just do a matrix multiplication with B to find all the unknowns, right? So I don't need to sort of go through all the Gauss-Jordan elimination process, row reduction process. I can just deal with matrices. So even if the size grows, I will be able to do this. So if you're using sort of a program to do this inverse, you can just form a matrix in, say, MATLAB, for example, and use an inbuilt function in MATLAB to find the inverse of that matrix, and then do a multiplication with B. No matter what the size of the coefficient matrix is going to be, you will find all the unknowns in X. All you need is that inverse function. Now, a very important note here, and this is sort of not intuitive, right? So let's try to take a look at this. In general, there's an important note, and this is for a general case. If you have AX, A is some matrix, and you're multiplying it with X, it is not equal, if that equals AY, if AX equals AY, that does not imply X equals Y. It is, however, true, it implies X equals Y only when A is invertible. So only when the determinant of A is not non-zero, only then AX equals Y implies X equals Y. But in general, it doesn't. So let's take a look at an example over here to prove this. A is a square matrix, 1, 2, 3, and 6. Those are your 2 by 2 matrix in A square. X is 3 and 1, a column vector. Y is a column vector here, again, 1 and 2. And clearly, X doesn't equal Y, right? So let's try to see what happens when you do AX, right? So let's see if when you do AX, what do you have? You have 1, 2, 3, 6, followed by 3, 1. This will give you what? 3 plus 2, 9 plus 6, right? And then similarly, if you do AY, what do you have? You have A is the same, and Y is 1 and 2. What do you get? You get 1 plus 4, 5, 3 plus 12, 15. So you see over here, AX equals AY. However, that doesn't mean X equals Y. Clearly we had X does not equal to Y. So AX equals AY, like here, doesn't imply X equals Y. Why do you think this? Why do you think that this was true? Well, this was also true because over here, if I look at this, look at the determinant of this guy. Determinant of A was 6 times 1 minus 2 times 3, 0, right? So when the determinant of A was 0, which meant that A was not invertible, that is the reason we had AX equals Y, but X was not equal to Y, right? So, but if A was invertible, then AX equal AY implies X equals Y. Questions about this? So I can say this is the reason, right? All right. Now let's try to see if we can find the inverse for a general case. This is for general n by n matrix. If it exists, can we find it? If it exists means what? The inverse exists, which means the determinant of the matrix is non-zero. So A is invertible, then its inverse, A inverse, will have to satisfy this property, A times A inverse should equal identity matrix. Then we can say that A inverse is the inverse of A. Now the process to find this is going to be to do a row reduced, to form an augmented matrix and row reduce it. So the augmented matrix is going to be A followed by the identity matrix. This, if A is n by n, right? So you see, if A is n by n, then the matrix that you're augmenting it with, I, is also n by n. So if you pad this, right, so you have A, then I, the number of rows will not change, but the number of columns would have changed to 2n, right? So the size over here of the augmented matrix is n by 2n, and we will do a row reduction process to get to a reduced row echelon form. If we go all the way to row reduced echelon form, what do we have? This particular A, as you are doing all those manipulations, will go to an identity matrix, right? So this one will go to identity matrix. As you're doing the reduced row echelon form. But as you're doing the row operations, you would have probably changed this as well. And that is going to appear instead of B. So you see what we are doing here. We are starting off with AI. You're forming the augmented matrix with the coefficient matrix on left and the identity matrix of the same size on right. You're going through the reduced row echelon form such that instead of A now, you have I, right? You have made it row equivalent to an identity matrix. And because of the row operations, you would have changed I to some other matrix B. And then B is simply the inverse of A. We'll take a look at an example, and then we will try to see whether it is true in general or not, right? So I'm going to assume some A. I'm going to form the augmented matrix. Then I'm going to do the the row reductions, go all the way down from A to I, and then whatever changes I would have made to the other identity matrix would give me my inverse. Let's try to take a look with an example over here. So an example to find an inverse. I'm given a 3 by 3 matrix A. I'm assuming that it is invertible. Assume invertible. Actually, let me just tell you guys how to find the inverse of this. Very quickly, we can validate that. So determinant of A is going to equal, and I can do this by using any row or any column. So I'll use the first row to do this. What I do is I will take this and find the determinant of the submatrix. The submatrix is going to be for that. If I eliminate that row and that column where the 1 is, if I eliminate this and this, I get its submatrix. The submatrix hence is going to be over here. So 1 multiplied by the determinant of the submatrix. This is going to be negative 13 minus 0. I do the same thing for all the other elements in my first row. Negative 3, right? For the second one, I do a negative sign. So let's take a look. For here, I'm going to remove this row, this column. My submatrix is going to be here and here. And I'm trying to find the determinant of that. So negative 3 multiplied by 0 minus 4. And then the last one will be, you see, if I erase this, if I am going to consider negative 1, I have negative 1 here. And then I remove these two, the same row, same column, and then look at the submatrix. The submatrix is going to be here, which is going to be minus 2, right? 0 times 0 minus 2 times 1 gives me minus 2. And if I find this, I get negative 13 plus 12 plus 2, which is going to equal, what is that? Negative plus 1, right? Which more importantly, it is not equal to 0, which implies A is invertible. So this is for a 3 by 3 case to find the determinant. We'll look at more examples later on, but I just wanted to point that out since we are considering a 3 by 3 example. So it is invertible. I've assumed it, but also I've proved it. Let's see. I'm going to set up AI. So I've got the A matrix, then I'm going to need the I matrix. So what am I starting off with? I'm going to do this in the next slide. Let's say I have after here. So set up AI. So A here, then I here, right? So A is going to be 1, 3, negative 1. Then I have 0, 1, 2. Then I have 2, 0, negative 13. Oh. And then I'm going to pad it with the identity matrix. Because A is 3 by 3, I'm going to use a 3 by 3 identity. So I've got, let me write that in blue. 1, 0, 0, 0, 1, 0, 0, 0, 1. 3 unit vectors with ones in the principal diagonal. Now I start with this, right? Let me, for the sake of clarity, let me also color code this. So I've got A, then I've got I. Now I'm going to row reduce it, right? So if I row reduce it, I'm trying to attack this, right? Let me show you what I'm trying to do. I am trying to row reduce this. So the goal is row reduce A such that it becomes row equivalent with identity, right? So essentially I'm going to try to get this over here, right? And for that I would have had to make some row operations, and those row operations would have changed this, and that matrix on the right would be the inverse of A. So let me just try to do the row reductions over here. I formed the augmented matrix. The first step I'll do is row 3 minus 2 times row 1. And if I do row 3 minus 2 times row 1, I'm going to have 1, 3, negative 1, 1, 0, 0. Row 2 also remains the same. And then I have row 3 that changes to 0, minus 6, minus 11, minus 2, 0, 1. Then I have row 3 plus 6 times row 2, which is going to give me row 1 doesn't change, row 2 doesn't change, row 3 will change. Next, I'm going to add a slide here. I'm going to continue that. Next, our row operation will be row 1. Row 1 plus row 3. I'll also do row 2 minus 2 times row 3. And that will give me 1, 3, 0, negative 1, 6, 1, 0, 1, 0, 4, negative 11, negative 2, next negative 2, 6, 1, and then I will do my last row operation, which is row 1 minus 3 times row 2, which is going to give me 1, 0, 0, negative 13, 39, 7, then I've got 0, 1, 0, then I have 4, negative 11, negative 2, then I've got the last row here in -2, 6, and then 1. Right. So you see, this has now become row equivalent to A, right? So let me just point that out here. Our A matrix is now row equivalent to identity, in this case I3, which means that all of the things over here this is my A inverse. So A inverse is simply -13, 39, 7, 4, -11, -2, -2, 6, and 1. So I hope that you guys are able to follow along with the process here. You see, when we started, oh, let me go back. What happened? Right. We took the matrix A, we formed the augmented matrix with the identity, we went through the row reduction forms, we wanted to make this row equivalent to identity. So that's why we made these particular row operations. As we were making the row operations, that side of the matrix, the identity was changing as well. And eventually, when we had a matrix that was row equivalent to identity, we ended up with the inverse of A on the other side. Questions about this process? Now, you don't need to do this for the 2 by 2 case because 2 by 2 case was straightforward. You were able to do it directly. But if you did, you would do something like this, right? You would form AI. Let me use red here, right? And that would be something like this. You would have A, B, C, D here, and then you would have 1, 0, 0, 1 there, and then you would do row operations, right? And your goal would be to make this into an identity matrix. So eventually you will get something like this. You will get 1, 0, 0, 1, provided it is invertible. If it is invertible, then you will get this 1, 0, 0, 1. And on the other side, you will have, and I know the answer, so I can write this. You will have D divided by AD minus BC. You will have over here minus B divided by AD minus BC. Over here, you will have minus C divided by AD minus BC. Over here, you will have A divided by AD minus BC. Let's see that. And so which means that all of this is going to be the inverse of A, right? So I've already included the determinant here. Determinant is in the denominator for all these guys. Okay. No questions? Okay. We can also check it, right? So we have started with A, you have found A inverse. So the way you check it is by looking at the product of A with A inverse, or you could do A inverse times A. Both of those products should go to identity, right? So if that is the case, then we know that whatever we have worked through is correct. So what I'll do is I'll go back here and I'll pick this A inverse. And I will bring this back over here, put it in here. That is my A inverse, and my A is over here. I'll use this. Right. So the claim was that that is the inverse of A, and the way you check it is by using the product of these two. So A times A inverse would be all of this Come on. Multiplied by all of this. And the claim is that this will get to, and if I've done everything correctly, this will go to an identity matrix. So let's try to just pick one case, just to be safe, to check whether you get it or not. Right. So for example, how do I get this value here, 0? Right. If I wanted the second row, third column entry in the product, then I would need to consider second row of the first matrix and the third column of the second matrix, and then do a dot product between them, right? So if I did the dot product between them, what do I have? I have 0 times 7 plus 1 times -2 plus 2 times 1, right? And you can see that it'll go to a 0. And similarly, all of the other things would be satisfied. They will satisfy as well. All right, questions about how do you find the inverse of a matrix? This is a general case, right? So the example that we have done, well, over here we did 2 by 2, but the example that we did completely was a 3 by 3. But I hope that you can see that you can expand this to 4 by 4, 5 by 5, any size, right? So all you need to do is form the augmented matrix A, I, do the reduction so that you get I, B, and then B is going to be the inverse of A if A is invertible. So this sort of process applies to n by n, any square matrix. All right. We did this. Okay, we did this. All right. Why does this work? Right. So the question is, why does this particular process of row reductions and making a row equivalent to identity, why does this work? And on the right hand side, you have the inverse of it. Why does it work? So let us say we wanted B, to find B, which is the inverse of A. Then we know that this is going to be satisfied, which is AB equals I or BA equals I. So suppose we are after B, right? So for the sake of this discussion, I will assume some A and some B, right? So let's say if I have A as some matrix A, I'm just going to leave that as is. And for B, I will assume that it is a matrix, and I'm going to consider, say, a size of n by n, and I will say this is going to be B11, B12, so on up to B1J, so on up to B1N, right? So that's my first row in B. Then I have second row in B, which is B21, B22, B2J, so on up to B2N, right? And I can do this all the way to, say I include even the ith row. So if I include the ith row here, I get ... Bij. And I can now write the last one. So this goes down. For the last one, I have Bn1, Bn2, Bnj, Bnn, right? The reason is I'm trying to focus on the jth column of I. So if B is the inverse of A, then I can write A times B is identity matrix. I've assumed this to be A and this to be B. I know that the result of AB should be identity, and I'll write that identity over here. So identity matrix is going to have what? It is going to have a bunch of unit vectors, right? So the first unit vector will be 1 followed by a bunch of zeros, n zeros, and that next one is going to be 0, 1, zeros. And for the jth column, what are you going to have? you're going to have 0, 0, 0, and then j somewhere, 1 somewhere, and then zeros will continue. And then this series will go through. The last column will have a 0 up front, but it'll have a 1 all the way at the bottom here. Right, so let me just clean up. Let's see. I don't want to write that. So I have a 1 there. Zeros will continue, and then you will have a 1 there. Then you will have a bunch of zeros all the way to the end, right? So this is my jth column that I'm considering. Now, for the jth column, how do you get that particular one? So focus on this one. How do you get this particular one? Well, that particular one is some row I, and column j, right? So row I, column j, you took row I in one A, right? That particular element is computed by taking row I here and column j here to get that particular one over there. Now, if you expand this to this particular unit vector, what should I call this particular unit vector? So I call this guy E1, right? So I call this guy E1. I call this unit vector E2. So consequently, the jth column I should call EJ, right? And then the last one will be EN. These are unit vectors. Unit vectors are vectors in which there is only one, and the location of that is corresponding to the subscript E1, E2, E3. Second element is 1, third element is 1, jth element is 1. So the way you get this particular column EJ is going to be the matrix A multiplied by the column J of matrix B, right? So what we can say here is matrix A, which is the size n by n, right, multiplied by B, Bj. Bj is the jth column. So this is the jth column. A is the entire matrix. And it is going to be okay because you see A is size n by n and Bj is going to be a column vector. Number of rows are n, but the number of columns are 1, right? So the inner dimensions match. What will this equal to? When you multiply A with Bj, A is the entire matrix, Bj is the jth column in B. When you multiply them, you are going to get Ej, right? You can see that you're taking the entire matrix here and you're taking each column here in this. If you take entire matrix multiplied by this, you get that. So that's what we are writing over here. A times Bj, the entire coefficient matrix multiplied by the jth column in B will give you the unit vector with 1 being in the jth column. So first entry, second entry, the jth entry will be a 1 here. All the others will go to a 0. So that's what I mean by focus on the jth column. You're focusing on the jth column of the identity here. And that is being obtained by taking the square matrix A and multiplying it with the column Bj. Next. So this is what we looked at. A multiplied by jth column in B gives you the unit vector Ej. So for each column of J, you have B equals inverse of A. So if A is invertible, then we know that A is invertible means A is non-singular, it is row equivalent. So all those 5 conditions. If A is invertible, then I can also say that A is going to be row equivalent to identity. So if you have row equivalent to identity, what we can do is we can form this particular matrix A with Ej. That's going to be your identity matrix, which corresponds to this particular system, Ax equals Ej, Ej being the jth unit vector. As you are doing the row reductions, what are you going to get? Because I know A is invertible, I know that A is going to be the row equivalent to identity, which means that if I start with A EJ, A is the square matrix, EJ is a column. So the size of this is going to be n by, so they are going to be n rows, but in terms of columns, it will be n plus 1, right? So that's the augmented matrix we are starting off with. If you start off with this and do the row reductions, because I know A is invertible, I know that you will be able to get to I over here. So if you get I over here, you are going to get some C over there, right? Because you see what is happening. You have all these coefficients here. You have a bunch of zeros and a 1 there. As you're doing the row reductions, those values would have changed. This is not homogeneous. This is EJ. It's a unit vector. So there is a 1 there. So those would have changed to some C. So what we get is I and then C for some vector C, which means x equals C will solve AX equals EJ. So that row reduction process can be written this way. Coefficient matrix followed, or A matrix followed by a jth vector, any unit vector, can be row reduced to I followed by B sub j, or C in our example. So if this is okay for each vector, you could say that for not just jth column of identity, you can say that for EI, E1, E2, E3, and so on. And what you're getting over here is B1, B2, B3, and so on. So those are specific columns in B. So if you put all the unit vectors together at once, A is A, all the unit vectors EJ will make I, then you can row reduce this to I, and then BJ, if you combine all the columns in BJ, what do you get? B. B is going to be your A inverse, right? So this works because if A is invertible, then you will be able to find a row equivalent identity matrix that you can reduce A to. That is why that particular process of finding an inverse of n by n matrix works. All right. Let us answer another related question. What if A is not invertible, which sort of implies that determinant of A is equal to 0, right? So if A is not invertible, then we will not be able to recover any an identity matrix in the first n columns, which sort of implies that A is not row equivalent to identity. And we'll take a look at an example here where that happens. If A is not row equivalent to identity, we know it is not invertible, we know it is singular, we know the homogeneous system will have non-trivial solutions. We know all of that based on the 5 statements. So let us try to look at a matrix A over here, and we are going to show the following matrix is not invertible. So let us see what happens when you start forming the augmented matrix and doing the row reductions. So if A is a 3 by 3 matrix, then you can form the augmented matrix as such. You have A over here from here, and then you have, because the size is 3 by 3, you will pad it with an identity matrix which is 3 by 3. Then you will start doing the row reductions. If you do all the row reductions properly, you will have something like this. So you see what happens here. You got 1, 0, 2, 0, 1, 0, 0, 0, 0. Your last, you were never able to get a 1 over here. Which means, so this indicates that it is not row equivalent to identity matrix. In this case, 3 by 3. Right. So if it is not row equivalent to I3, we will not be able to recover from the first 3 columns. Identity cannot be recovered using the first 3 columns. It is not row equivalent, which means that it is not invertible. So this is not A inverse. We will not be able to find A inverse. A inverse doesn't exist in this case. So now I can also prove it slightly differently. I can try to find the determinant of this guy and it will equal 0. So let me just check that over here. And if I expand using the first row, as I did earlier, I will do determinant of A, right? So I'm trying to do this first. 1 times the determinant of the submatrix, which is going to be 2 minus 4. And then I do minus 0 times whatever. It's going to cancel out anyway, so I don't even need to write that. And then the last entry is going to be 2 times. So for this 2, I will have this submatrix there. So that is going to give me 2 minus 1, 1. Right. So, and you can see that this is going to equal negative 2 plus 2 equals 0. Right. So that also indicates that A is not invertible. And you can see for those matrices, when you do the row reductions, you will not have row equivalency with the identity matrix. So this, if you did this, this actually doesn't just mean that A is not invertible. It also means that A is singular. It means that the homogeneous set has non-trivial solutions. It also means that AX equals B cannot be, you cannot find A inverse times B to get the solution set for X. All right, now let's try to work through some examples here. We are going to try to find conditions on the vector for the right hand side, which is B in our case, for a system to be consistent, right? So what conditions must these constants B1, B2, B3 satisfy such that the system of linear equations over here is consistent? So we are going to do some row reductions over here to see whether we will be able to find that the condition on B. So I'm going to start with the augmented matrix. So I'll see over here. I have the coefficients of x1, x2, x3, 1, 0, 2. And then for the right hand side column, I have B1. That's my first row in the augmented matrix. Then I have 0 for x1, 1 for x2, then 2, then B2. Then I've got 1, 1, 4, B3, right? So that's my augmented matrix, and I'm going to start doing row reductions to see what happens for consistency of the system. So the first step I'm going to take is I'm going to try to eliminate this one over here. So I'll do row 3 minus row 1. What I'll get is 1, 0, 2, B1, 0, 1, 2, B2, 0, 1, 2, B3 minus B1. The next step I'm going to do is I need a 0 here. So for that, I'm going to do row 3 minus row 2. And when I do that, I'm going to get 1, 0, 2, B1. I'll have 0, 1, 2, B2. Then I'll have 0, 0, 0. Last one will be, let me write that in black here, B3 minus B2 minus B1. Now, for the checking the consistency of the system, we know that it will be consistent if all of this will go to a 0, right? Otherwise, we'll have 0x1 plus 0x2 plus 0x3 equals that. So for consistency, we know that B3 minus B2 minus B1 should be equal to a 0. So I can write that system is consistent if and only if B3 minus B1 minus B2 equals 0, right? So only then I will be able to write that. Now you can take a look here. That is the condition, right? So any vector B that satisfies that, you will have a consistent system. So for example, if you looked at B example, if vector B is 3, 2, 5, for example, what do you get? 3, 2, 5, let's check for consistency. B3 minus B1 minus B2. 5 minus 2 minus 3 will give you a 0, right? So that means that this is going to be a system that is consistent. So if you plug in over here 3, 2, and 5, you will have these values change, right? So you will have these values will go to 3, 2, 5. These values will go to 3, 2, 5. Over here you will have 3, 2, and then 0 over here, right? So if you have 3, 2, 0 over there, so let's take a look at it on the next slide here. So if the vector B is 3, 2, 5, what is my augmented matrix going to change to? It will change to 1, 0. So let me just copy this. Over here. And I'm going to substitute for B1, B2, B3, which is 3, 2, and 5. So my matrix is what? 1, 0, 2, 3, 0, 1, 2, 2, and then I have zeros, right? So if you look at this, what can you tell me about the solution set? Well, you can back substitute and find that out. From the last column, I don't get any information, but from the previous two rows, I get x2 plus 2 x3 equals 2, and I will get x1 plus 2 x3 equals 3, right? So if I assume x1, x3, I'll assume x3 equals some arbitrary value t. In that case, I get x1 to be 3 minus 2t, and I get x2 to be 2 minus 2t, right? So the solution set would be many solutions, right? Infinitely many solutions here. System is consistent, but it has infinitely many solutions. The solutions will be what? Solutions will be the vector x. x1 is 3 minus 2t, 2 minus 2t, and t. Right. So for any arbitrary value there, you can plug in for t, 1, 2, 3, whatever, and you can find the solution set over here. So the condition, however, to answer the main question, what is the condition on B such that the system is consistent? Well, if you consider this set of linear equations, then the condition is this. Let me just do that. B3 minus B1 minus B2 should equal to 0. So for example, if you chose, the other example would be if you chose B to be, say, 2, 4, 1, then you would have no solution. Because it doesn't satisfy the condition for consistency. You see, 1 minus 4 minus 2 is non-zero. Okay, questions about this example? All right, let's move on to the next one. So let us try to look at a similar set of linear equations here. What are the conditions that B1, B2, B3 should satisfy for a slightly different set of linear equations? We will try to adopt the same strategy here. We will try to form the augmented matrix. The augmented matrix is going to have the coefficients of x1, x2, x3, and the last column will be B1, B2, B3. Then you will row reduce it, right? So you will start with this. Start with the augmented matrix. You will have 1, 0, 2, B1, and 2, 1, 4, B2, and the last one will be 2, 0, 3, B3, right? And once you have that, you will row reduce it. So as you are row reducing it, you will get, for this particular matrix, you will get this. So on the right hand side, you got to reduced row echelon form. The matrix over here is row equivalent to an identity matrix. The one column over here, as you did those row reductions, worked out to be negative 3b1 plus 2b3, negative 2b1 plus b2, and the last entry is 2b1 minus b3. So this is just one column there. So we know that the system is going to be consistent for any b, right? Any b that you have, because it is row equivalent here, for any vector b, which is, so b is what? b1, b2, b3. Any value that you pick, you will have values over there. So x3 will equal that, x2 will equal that, x1 will equal that. So you will have a solution. So system is consistent for any b in this case. But there is a little bit more to that. As you are, we did this. We took this particular A matrix, we reduced it. As we reduced this, we got this on the other side. So you took A, you took the right-hand side coefficients in B1, B2, B3, you did the row reduced echelon, the row reductions to get that. Now, it turns out that the coefficient of B, right, the coefficients of this are actually the inverse of A. The coefficients of B are what? Negative 3, 0, 2. Negative 2, 1, 0. 2, 0, negative 1. So those are actually the elements in A inverse. Since if you did A inverse multiplied by B, you would get back this particular vector over there. And you can check this. You can check this by finding A times A inverse. So A was given to us as 102, 214, 203, and A inverse, which turned out to be the coefficients of this, is negative 302, negative 210, 20, negative 1. You can check this and it will satisfy the identity matrix. So if you look at the second example, you have, so you see that's another way to find the inverse, right? So you have a coefficient matrix given by the coefficients of x1, x2, x3. The right-hand side constants are b1, b2, b3. You do the row reductions such that instead of the coefficient matrix, you have the identity. The coefficients of the b's that you will be left with are going to give you essentially the inverse of that coefficient matrix. All right, that is all I have for you guys in terms of matrix inverses. A couple of notes about the homework and the lecture quiz. I will be releasing lecture quiz number 7 this afternoon. So do that on Gradescope. You guys have done it for all the previous 6 quizzes, so it should be straightforward. And then homework 7 has also been posted, which is due on Tuesday. The homework 6 has been graded, so I'll publish those grades about homework 6 soon. All right, so let me stop the recording here, and if you guys have questions, I will take them now. Let's see.